So, hello everyone. Today I'm going to give a presentation um, on a multi-cluster stateful application demo using KubeFleet. So, I am a maintainer on KubeFleet on the KubeFleet project, and then um, we are a CNCF sandbox project, and the project's main goal is to help multi-cluster application deployment. And I want to do this presentation on stateful application demo because I know that most of our users are using stateful application, but the KubeFleet project itself does not really consider whether the application is stateful or not. We have a lot of features allowing people to using a certain labels on the member clusters and allow people to pick and choose the correct, the most appropriate member cluster based on certain properties to run your application. But we are not really considering whether the data are getting replicated to those member clusters. So today I want to do a presentation or maybe just an experiment to see how do I use KubeFleet to run a stateful application, considering that we need real data application capability on our database. So I want to talk about multi-cluster stateful application challenges. Um, as I just mentioned, the number one challenge is that storage doesn't travel. Typically, to run a stateful application on Kubernetes, you either connect directly to a database that's not running on Kubernetes, or you use PVC, persistent volume claim, but that is cluster local. So it means that in a multi-cluster solution, you will need to consider how to replicate the PVC to multiple clusters. And then even if we replicated the PVC to multiple clusters, we still have to consider that the data represented by the PVC does not automatically get copied to multiple clusters by Kubernetes natively. So we have to handle that. And number two is that can have same manifest, so same Kubernetes YAML file, but we need different identities across multiple clusters. In the most typical use case, we will have one cluster serving as the primary data replica, and then the other cluster will serve as the um a read-only replica. And then even though these two data YAML manifests are mostly the same, but because this one serves as the primary and the other serves as a replica, there needs to be some customization based on which role the current cluster is playing. And number three is that this role coordination that I just mentioned, so primary versus read-only replica, has no built-in primitive. The Kubernetes itself does not really care whether the current cluster is a primary cluster or the current cluster is a read-only replica cluster. It doesn't have this concept, and then we have to, as users, we have to figure this out on our own. And last one, which is about replication lag. So whenever you set a database to be the primary replica, and then a different database in a different cluster to be the read-only replica, you would have to consider that there is some data replication delay from the primary to the secondary. And in my demo, I'm doing everything locally. just simulating two different clusters on two different regions. But in real production scenario, if you have one cluster on East US and another cluster in West US, the replication lag would be noticeable, and a cluster admin or a multi-cluster admin would have to take this into account. Otherwise, you'll be seeing data loss. So without further ado, let's get into the stateful failover demo that I prepared for this community call. Um, so the scenario that I'm trying to emulate here is that many companies need some disaster recovery plan. So even though their primary database is in one region, but for business continuity purpose, sometimes they will need to do disaster recovery exercise, whether it's an exercise or a real scenario, they would need to um, run the application away from their primary region in a secondary region where the data have been replicated asynchronously over the months. And then when a disaster happen, the application owners or the platform owners would have to stand up a different the application in a different environment in a different region, such that they can continue to serve their customers while the primary region is down. So that's the main motivation of this demo. And then let me go to the demo markdown file to briefly talk through the architecture. So in this architecture, we are going to use we are going to have a KubeFleet hub cluster. And this hub cluster only runs the Kubernetes KubeFleet control plane. It is responsible for scheduling Kubernetes YAML manifest across two different member clusters. One is a client cluster, which is what I use to simulate a US West region. The other one is another client cluster, which I'm using to simulate a US East cluster. And in the beginning, we have US West cluster as the primary replica and the US East cluster as a read-only replica. And both applications are backed by a Postgres SQL database. I choose Postgres SQL database because I know it's one of the most popular SQL database chosen by a lot of enterprise users. So I hope that this demo will be somewhat representative of what a real user is going to see. Okay, and then in this demo, I will be making use of different capabilities from KubeFleet, mainly the namespace scope placement capability, as well as the resource override capability. So a placement is a KubeFleet concept for representing the clusters that the deployment should go to. So later in the demo, you will see that how I will configure the placement object to say that I want my application to go to both of my clusters. And then the resource override is a custom resource created by the KubeFleet developers. Its main purpose is to customize the Kubernetes manifest deployed to different member clusters based on the role of the different member clusters. So as I just mentioned, my US West cluster will be primary first, and then my US East cluster will be a secondary cluster in the beginning of the demo. And then when a disaster recovery scenario happens, I will flip the rows of the two different clusters. So the US West cluster will become secondary cluster, and the US East cluster will become the primary cluster. And then the way that I flip the row would be to make use of the resource override custom resource. And then I will also be making use of the stage rollout capability of KubeFleet. The stage rollout capability is a recently GA feature from KubeFleet. So in the beginning, when KubeFleet was just started out, we only allow rolling update strategy, which means that if we successfully rolled out to maybe a couple regions, and then the KubeFleet scheduler would start sending the workload YAML file to the remaining regions, and then there's no wait time or approval um, configure between the member cluster rollouts. So that, but for any like production multi-cluster rollout, um, a rolling update like that doesn't really work because most users would prefer having a stage rollout capability where the users can say, I want to bake the rollout in, let's say, the Canary region for 24 hours before moving on to the production regions. And sometimes there must be some manual intervention um, between the earlier Canary regions and the production regions so that the users the platform admins, they can check whether the application is healthy in the Canary region before approving its release to the later regions. Okay, I'm gonna get started with the demo. Before starting with like the first step, I want to clean up the environment first. So just now I was testing the demo and then I created some local kind clusters. And now I'm just deleting them. Okay. First step, I'm creating the kind clusters. So as I just mentioned, we have a kind cluster representing the hub. And we have two kind clusters representing the member clusters, one in US West, one in US East. And the US West one will be my primary cluster in the beginning. And then US East will be my secondary cluster. And then this step is installing the hub agent on the hub cluster. And then I will be installing the member agents on the member clusters and then join the member clusters to the hub cluster. So a little bit of background on the hub and member agents. So the hub agent is the a set of controllers that live on the hub cluster, which are responsible for scheduling workload to all of your member clusters. Okay, this is completed. Next step, I'm going to label the clusters and build the images. So I want to explain this cluster labeling step here. So firstly, I'm labeling my US West cluster as US West region and a primary cluster. And then I'm going to label the US East cluster as a US East cluster region and a replica cluster. And here, I'm building the Docker images for the mock application, the sample application that I'm going to use to demonstrate this failover demo. So I will have a Postgres operator, initiator, Docker container, and then a backend Docker image, and then a front-end Docker image. And then I'm going to load those images to my member clusters. And note that I don't have to load those Docker images onto my hub cluster because the hub by design is not running any user workload. And now I'm going to deploy the YAML manifest to the hub. Even though I'm deploying the YAML manifest to the hub, um, because the hub by default has a webhook validation that stops pod and replica set from running on the hub. So I'm just applying the manifest on the hub, but no pod, no replica set will be actually running on the hub. And the next step is running the headlamp plugin that we built specifically for KubeFleet. I'm going to show you the headlamp plugin in 1 second. Okay, starting up the headlamp server. Okay, now let me refresh this page. So this is the KubeFleet Manager headlamp plugin. So headlamp, for those not familiar, is a Kubernetes open source Kubernetes UI, and then we can add plugin to the headlamp ecosystem, and then in this case we have a KubeFleet Manager plugin, which allows users to see their KubeFleet custom resources on this UI. Okay. Now I finished starting up the headlamp server. Oh, by the way, welcome, Yetkin. Thank you for joining. Now let's move on to the next step, which is I'm going to create a KubeFleet CRP. So cluster resource placement is a KubeFleet custom resource, which represents how we want to deploy how we select the member clusters that we want to deploy our application to. So in this case, the most important thing is placement type, pick all, which means that all the member clusters joining all the member clusters that are joined to the hub, we will place our application there. And then it also has a resource selector, which selects the namespace where my Kubernetes YAML will live in on the hub. And we are saying that we are going to deploy everything under the KubeFleet -pg namespace to all the member clusters. And the strategy here is external, which means that we are going to make use of the stage rollout strategy instead of the default rolling update strategy. I need to apply this YAML using the plugin, the headlamp plugin. Okay. And then you can also see that the cluster resource placement CR was applied. And then you can see all the properties on the headlamp plugin. And right now it's in a pending state because we choose the rollout strategy as external. So the rollout wouldn't get triggered immediately. It's going to wait for the user to create some more custom resource before it will start rolling out. And now I'm going to create some resource overrides. I probably have some environment variable that I didn't set on that window. So I'm going here. Nice. So here I'm labeling my primary cluster as the primary cluster, but I'm setting the container's environment variable as a primary. And then for the replica cluster, I'm setting the replica environment variable as well as the primary cluster's IP, because the read replica cluster would have to sync data from the primary database, and then it would need to know its IP. And then here I'm just labeling one cluster as US West and the other cluster as US East using the container environment variable. Okay. Now I'm creating the cluster stage update strategy. So the cluster stage update strategy defines that my rollout will have two stages, the primary stage and the replica stage. So I will deploy to my primary cluster first, then wait 30 seconds, and then I will deploy to my replica cluster. Okay. And then you will be able to see the rollout strategy here on the headlamp UI. And then I will also need to create a stage rollout run. I'll just do the YAML. So here I'm basically saying that I want to roll out the pg-app cluster resource placement. The cluster resource placements defines that I want to deploy everything from this namespace to all of my member clusters. And I'm also referencing a stage rollout strategy, which is the rollout strategy that I just defined, which says that there are two stages. I will deploy to my primary cluster first, wait 30 seconds, and then deploy to my replica cluster. Okay, I'm applying. And then now on the UI, you can see that the US West cluster deployment is in progress, and now it's waiting because the deployment finished, and we're waiting 30 seconds before we start the US East cluster deployment. Okay, while this is in progress, I want to introduce the next step, which will be that I will forward the application front end from both the US West cluster and the US East cluster to a local port so that we can see the front end visually on my browser. Okay, let me refresh. This one is in progress now and completed. Nice. Okay. Do the port forward. Okay, I think let me refresh locally. Okay, so now you can see that here we are looking at the US West cluster UI, and that's the primary replica. And then because it's the primary replica, we can modify data here. And the one serving on port 3002 will be the US East cluster, and it is serving as a read-only replica cluster. So I wouldn't be able to change anything here. We're gonna get an update fail, but I'm going to delete everything from the primary and then add something new here. And then we should be able to see the change reflected on the read-only replica. So here we prove that the data synchronization is working, and then the two UIs from two different regions are backed by the same data. I guess this is the primary copy of the data, and then this is the read-only replica of the data. Okay, now we have all the basic setup. I want to go into the disaster recovery scenario, or maybe just a region migration scenario where I will flip the the primary um, cluster to become a replica cluster and the original replica cluster to become a primary cluster. In order to do that, firstly, I would need to override the member clusters label. Okay, after labeling, and I would need to update the resource override as well. And the resource override, as I just mentioned, it is populating some environment variable on the pod because even though I label the clusters, the member clusters as primary and replica, um, there is some work need to be done to let the workload actually know that they are either the primary or the replica. Okay, the resource override is done, and now um, I can create a migration rollout. Notice that I don't have to recreate the cluster resource placement, which defines which clusters my workload should go to. And then I also don't have to recreate the cluster rollout strategy because I'm going to reuse the same two-stage process, where the stage one will be US West, and then the second stage will be US East. Okay, I'm applying the stage update run, and now we should be able to see two stage update run. The first one was already completed, the PG deploy 001, and then the second one is what I'm going to do right now. I'm going to run right now. So it's already in progress. Um, it went to US East first. Oh, I think I just said it wrong. It went to the US East first, and then now it's waiting. It's still waiting 30 seconds. And then after 30 seconds, we'll proceed to US West. Okay, now US West is in progress. US West done. Okay. Um, now we can verify the result. So let me refresh the US West UI. Now you can see that the US West UI is no longer a primary replica, but a replication. And then if you change the number here, it wouldn't work because the backend Postgres SQL database is a replicas database. So you cannot update a read-only replica. But on the other hand, the US East UI becomes the primary replica. And then I can actually make some changes here. Okay. Maybe reads. Okay. And then if we go back to the replica cluster now becomes US West. We should be able to see the changes getting reflected here. And so this concludes the presentation on the demo. So just in conclusion, what I just demonstrated was how you can use KubeFleet to orchestrate a regional migration workflow or a disaster recovery workflow where you had a primary region where your application was running, and then it is backed by a stateful database. And originally, the setup was that your secondary region was synchronizing data asynchronously from the primary region. But after the migration, I am making use of KubeFleet cluster resource placement as well as um, resource override custom resources to fail over or move the primary to a different region. And now you have, at the end, you have the primary running on the new region, and the original primary region becomes a read-only replica region. And that's it. Now let's go back to the slides. Um, this concludes my demo. And if you guys have any question, you can ask. I think so after doing I think in the beginning I said that this demo was mostly just an experimentation because when we are designing or like working on KubeFleet, we don't really consider like whether the application we use is a stateful application or a stateless application. We just assume that the users are going to handle the data replication themselves. I think it is still true today. Throughout my demo, like KubeFleet just deploy your YAML to US West and US East. You can use resource override to label your clusters differently, but KubeFleet doesn't really have a lot of features to help you with your data synchronization. You still have to set up your Postgres operator to do the data replication correctly. And then if you think about like for example, number 4, challenge the replication lag, challenge KubeFleet doesn't really care. If you are a cluster admin, um, you would have to make sure that your you would have to first cut off any incoming traffic to your primary region, and then wait until your secondary region catches up with the data replication, and now you can do the failover. Otherwise, you're going to lose data. And KubeFleet doesn't handle this natively. And so I think there are still quite some gaps in how to make this this behavior like more more streamlined for the users. Maybe we are going to do it. Maybe it is too difficult. I don't know yet, but we are looking forward to like any suggestions, any ideas on how we can make a multi-cluster stateful application running more smoothly on our KubeFleet. And here are our community links to our repo and to our community core repo. So I'm going to send this links to the chat, and then if there's no more questions, if there's no question, I'm probably going to end here.